This video is to make up for the drop connection that we had this afternoon. And today our topics are simple harmonic oscillators, phase shifts, energy in simple harmonic oscillators, and the physical pendulum. So yesterday we had derived, we used differential equations to show how both a mass on a spring and a pendulum would have a characteristic frequency. And we modeled the functions using sine and cosine. So if I was to write something like this, a sine theta, then this could produce a position for x at a given angle. But this is kind of weird because if I have a mass bouncing up and down on a spring, I don't really have an angle. So what does the angle really mean? We know that the sine needs to take an argument of radians. So if I was going to have a function that ran with time, then I would replace theta, which is an angle. We need an angle to be an argument for the sine function, with omega t. And so this could now predict the position at any time t, because we also know that with this simple harmonic oscillator, that we need something here in this argument that reflects the periodicity of the motion. Now this is inverse the period because something with a high frequency is going to have a short period. But anyway, we need something that reflects how often this motion is going to repeat itself. Now, if you wanted to think about this in a slightly different way, we could go ahead and I set up a motor here. I described some Legos and the EV3, and I'll zoom out just so we can see what this looks like. And I set the motors so they're on a low speed. Now, if I flip this over and now consider the motion from the vertical standpoint, then I'll allow my finger to just follow this back and forth. So the horizontal component of this is oscillating back and forth. And it's oscillating back and forth with the angular frequency that matches up with the angular speed of this wheel. And as we expand out this idea, so that's why we use omega in here. So it does reflect the speed at which things are oscillating, and we can connect it back to what the period is going to be as well. Now, the most general that we could do the most general form would be, if I was going to include all the different possibilities, would be x is a function of t, and I have the amplitude out front, so this modulates what the range of motion is, and then sine. But just omega t assumes that the clock starts right when the displacement is equal to 0, and I can't really guarantee that all the time. So sine of omega t plus the Greek letter phi, where phi represents a phase shift. So by putting an additive constant at the end, this is the vertical shift. And then this is a horizontal shift. All right, so that's the most general case. Now, if I take the derivative of that to find out what the velocity is going to be doing, then one factor of omega comes out, and derivative of sine is cosine. So this is going to be omega a cosine, and then omega t plus the phase shift plus whatever the initial velocity is. However, I also know that I can write cosine in terms of sine because cosine of theta is equal to sine of theta plus pi over 2. So that equals omega A sine, and then I'll have 3 terms in here, omega t plus the phase shift plus pi over 2. Now for the acceleration, I take the derivative of the velocity. So another factor of omega is going to come out, and then I'll have a minus sign. So this will be minus omega squared A sine omega t plus the phase constant plus V0. But the relationship with negative sine and sine is that negative sine of theta is equal to sine of theta plus pi. So that means I can rewrite this. I get rid of the minus sign and rewrite it as omega squared times A times sine of omega t plus Greek letter phi plus pi plus A0. Yeah, this should have been an A back there. So the implication here is that they're all going to have the same frequency, but they'll differ in a phase shift. So let's take a quick look at that.